All right, so today we're going to start off talking about equilibria. Equilibria, you guys have covered in Gen Chem. However, a lot of people still have some misunderstandings of what an equilibrium actually is. So let's try to come up with the definition of equilibrium on your own, and then I want you to check with your neighbor and see if you guys are coming up with the same concept for what an equilibrium is. So let's discuss it with the partner.
So it's not that it doesn't ever change, it's constantly reacting, but overall you're not changing I hope so. Now when it comes to math, I make it really hard.
All right, who thinks that they've got a pretty good definition of what an equilibrium is? What do you think, Brian?
A state of dynamic stasis with both there's two reactions, a forward and backward reaction, that are occurring, and they are both equal and opposite, so there is no net change.
Okay, so there's no net change. In rate, concentration, what are we looking at when we're saying there's no net change? Yeah, concentration of products over reactants. A lot of you guys remember that KEQ equation, right? So an equilibrium is really when you've got some concentration of products over some concentration of reactants that doesn't change. It's basically staying steady the entire time. Oftentimes people will call this a dynamic equilibrium. One question I have for you guys is that's kind of abstract. Does that mean that the reaction stopped? No, and that's one of the biggest misconceptions people have. And I like showing people this demo here. So let's say we've got this reaction coordinate diagram, and as you can see down here, I've got this little green A, and then I've got this molecule here, and then it goes to AB plus C. And I'm just going to plug in a bunch of molecules on one side. So let's say we've got 50 of the green balls in solution. And then for BC, that red ball and blue ball, I'll put another 50 in. What I'm going to do is put no products in. So we're going to pump this into our chamber. And then it's just going to bounce around. What I want you guys to notice, though, is on this side, over here, where there's A, B, and C. You notice how we started at 50, but it's going from 44, 43, and it's going down, and the other side's increasing. Let's add in a little bit more heat so we can speed up this process. So if you notice, we're going from 47, it's going down to 40, it's going down to 30. We'll wait for it, we'll wait for it, we'll wait for it. Now we've got roughly 25. Everything's still bouncing around. You've got some going to the product side, some going to the starting material side. Everything's dynamically occurring in solution. But can you see how the concentration of A, B, and C aren't really changing when you look at the average of them? They're fluctuating slightly, but the overall average is roughly the same for the starting materials and products. We know we're reaching equilibrium when the concentration stops going up for one or stops going down for one. It's reaching that steady state. So let's go back to our notes and kind of diagram what this means. It is a condition where the concentration of your products and the concentration of your reactants stops changing. It's important to note that the reaction still occurs, it's just that concentration stops fluctuating. Another way of viewing this, too, is let's say we've got two things in solution. We've got A plus B, and we've got this equilibrium, and this goes to C plus D. Another way of viewing this is you've got two competing reactions in equilibrium. You've got K forward, where you're going from A to B plus C to D, and you've got K reverse. In this case, what do you think the relationship is between K forward and K reverse at equilibrium?
Equal magnitude of zero.
Yeah, they cancel each other out. So in this case, they'd be the same, but in opposite directions. So the reaction going in the forward direction is going to be the same rate as the reaction going in the opposite direction. It's a little bit weird to think about. All right, so let's define this using our KEQ. This is our equilibrium constant. We know that KEQ will be what here? Do we do concentration of C plus D? Times. So we do concentration of C times concentration of D. Those are our products over the concentration of A times the concentration of B. So at equilibrium, this ratio stops changing. All right, another way I like to view this is, let's say we've got a reaction coordinate diagram. And I've got Gibbs free energy on this axis. And at this position, I have only A plus B. And at this position, I have only C plus D. So let's imagine we have only A plus B. That's not going to be very stable in that equilibrium, right? Instead, it's going to want to drop in energy. And then once it hits this equilibrium point, you actually hit this well of energy. And then once you start climbing up towards the C plus D side where you lose all of your A plus D, you go out of equilibrium. So equilibrium occurs at this point. The interesting thing, too, is technically every reaction can be viewed as an equilibrium reaction, right? Some equilibriums are more equilibrium-like than others are. Oftentimes we show reactions with a one-way arrow. What does that mean?
That equilibrium basically null.
Yeah, it's a little weird to think about it, but if we show a reaction with a one-way arrow, there still is a potential of a backwards reaction, but it's so negligible we don't even bother drawing it as an equilibrium reaction anymore. So we talked about that with acid-base chemistry, where we said if you've got a pKa difference greater than like 5 or 6, it's really just a one-way arrow. It's not really an equilibrium of acid-base chemistry anymore. Same's true with just about any reaction.
Just a quick question on the equation for this. If we had coefficients, they would go as the powers, right? We raise the power for these concentrations. So concentration A, like coefficient 2 would be squared, right?
Exactly. So the question was, what if we had 2A? Then we would need to put a subscript 2 in the front. Yeah, that's correct. Okay, so let's talk a little bit about an equation I'm sure you guys are familiar with. How many of you guys remember the Hoff equation? You guys thought you got away from it. I did not sign up for math. I thought this was okay. So let's take a look at the Hoff equation. We can now relate our idea of Gibbs free energy that we discussed yesterday to equilibria by using this equation. So it's delta G equals negative RT natural log of our equilibrium constant. So let's write down what these values are. Does anybody remember the gas constant value, R?
8.214.
Yeah, in this case it's going to be 8.314. And this is typically in joules per mole Kelvin. Okay, and then we have temperature, which is always measured in Kelvin. And then we've got this KEQ equation, which we already said KEQ is going to be equal to our concentration of our products over our concentration of our reactants. All right, now let's reorganize this. What if I want to solve for KEQ and have that isolated on one side of the equation? Yeah, then we have to do some algebra. So if we reorganize this and solve for KEQ, then it would be E raised to the power of delta G over negative RT. So depending on what you're going to solve for, whether that's delta G or KEQ, you want to pick the appropriate equation. All right, now we've got a thought experiment. The thought experiment is, let's say we've got this reaction, where we've got our reaction coordinate. And I've got my starting materials here and my products over here. We've got some sort of energetic barrier. But in this case, delta G is 0. What is KEQ? Pretty easy, right? 1. All right, let's check this with math, though. All right, so let's solve for KEQ. So in this case, we're going to say KEQ equals E raised to delta G over negative RT. Okay, so let's finish this equation just for the sake of argument. All right, E to the 0 over negative RT is always going to be E to the 0 power, right? E to the 0 power, if you plug that into your calculator, is going to be 1. So if we think about this, that means that KEQ is telling us that our ratio of products over reactants is equal to 1. Another way of saying this is we've got 50% product in solution and 50% of our reactants, right? You guys want a harder one? All right, let's do a harder one. We'll test our math skills.
Is that what is KEQ1, or is that what is?
It should have been what is KEQ question mark. Sorry. My brain was going too fast. All right, now let's do a harder one. Let's say I've got this reaction. I've got delta G, and in this case I've got my starting materials up here, and I've got my product down here. So in this case, our delta G is measuring this difference in energy between our starting material and products. And let's say in this case it's going to be, I don't know, let's say negative 20 kilojoules per mole. Now the question is, what percentage of the equilibrium is product? So now we're going to have to use some math to solve this. So I'll give you guys a minute to work on this, but then try to check with your neighbor and see if you guys are coming up with the same answer. That's a good question. What's our standard temperature? In Kelvin? 298. So let's make an assumption. This is the same assumption you'll need for your pod. Is assume 298 K for your temperature. That one? All the way up?
Oh, sorry, I was just.
What is 0 Kelvin? Is it 273? I mean, 0 Celsius? Or 0 degrees Celsius, is that 273
You go
Kelvin?
back there.
Yes.
So why are we saying 29?
So room temperature is 298, roughly. I mean, that's your average. So 298 assumes 25 degrees Celsius, which is about the standard temperature of most rooms.
Well, depending on what you do, sometimes it's like 20 degrees, sometimes it's 25.
Yeah, it depends if you live in Thailand or Alberta, I guess.
For our purposes, it's 25 degrees Celsius.
All right. How many people think they at least solved the math, or a couple people need more time? Let's spend a little bit more time on it, but I'll start plugging numbers in. Question for you guys. Why did I change 20 kilojoules to mole to 20,000 joules per mole? Yeah, if we look at our gas constant is in joules, not kilojoules. So that's a simple mistake a lot of people make, is they forget to make sure all their units cancel correctly. So I'll just quickly on the fly multiply it by 1,000. Let me actually move this down. There we go. How many of you guys got a number? A few people? What's up?
I'm looking at my sig figs. Negative 20,000 is one sig fig.
In this case, I'm not concerned with sig figs. This is more just a thought experiment.
Cool. Stop and pop. So I gotta remember that.
All right, how many of you guys got a number?
KQ.
All right, it looks like most of us are getting numbers. How big is that number? Is it small? Did you guys do the E portion?
I got a pretty big number.
Wait. Oh.
Big relative, but I mean,
Oh. Does anybody have a number they want to share?
I got 32 at 4.885.
So about 3,200?
Yeah.
Okay, I agree with that. We'll say 3,205. What are our units here?
There's no units to cancel out.
No units, right? So all the units cancel out, so our KEQ is going to be 3,205. Now the question was not what was KEQ, but rather it was what's the percentage in equilibrium that's product? So let's do a little bit more of this problem here. So we know that KEQ equals 3,205. And we know that KEQ is going to be equal to our products over our reactants. Okay? So let's think about it this way. We could say 3,205 over 1 is equal to our products over our reactants. How can we solve the percentage of products in equilibrium? What do you guys think? An ice chart? No, we don't even need to do that. Mm-hmm.
Just be 3205 over 3206.
Yeah, exactly. This is something that people really overanalyze. I'm basically telling you that our product's concentration is the 3205 number, our reactant's concentration is 1. So if you think about this, our ratio of products over our full reaction mixture, which is our products plus reactants, times 100 will give us our percent product at equilibrium. So let's try this. We know our products in this case are going to be 3205. We've got 3205 plus 1 times 100. So let's plug this into our calculator.
99.97.
Yeah.
All right, so I'm getting 99.97, we'll say. So if we think about this in terms of a practical point of view, if our delta G value is negative 20, is this much of an equilibrium? No, not really. If we're doing a reaction where 99.97% of the solution is your products, that's not much of an equilibrium. So this is a unique way of showing that when delta G is less than negative 20 kilojoules per mole, the reaction is essentially a one-way arrow. Meaning it's not really at equilibrium much anymore. It's essentially all going to products. It's not really going to push back to that starting material side very much. Yep? Sorry, that's supposed to be a less than. Meaning if it's negative 20, negative 25, negative 30, it's going to essentially only favor products. Yeah, I mean, it's one of these things where it's an approximation, right? Negative 20 is kind of my general idea. And a lot of people are like, well, is negative 20 large or is it small? Let's go back and look at our bond dissociation energy table, because right now that's just a number. If we look at our bond dissociation energy table in kcals per mole, you see how most of these kcals per mole are in the hundreds? So what we're dealing with is a situation where equilibria really only occur under a small window where you've got a delta G value that's roughly within plus or minus negative 20. That's the window at which we really are concerned with the backwards reaction occurring too. Does that make sense? Otherwise, it's just a one-way street for the most part. Equilibria is just a plural. Yeah, so equilibria is more than one. So if we're talking about the general concept, I tend to use equilibria. Equilibrium is one example. So when you're at equilibrium, that's when the concentration stops changing. So your concentration of products and your concentration of reactants doesn't fluctuate anymore. It's more or less holding steady, but in a dynamic situation. I know this is kind of abstract to think about, but my goal is for you guys to be able to anticipate when a reaction's at equilibrium or not really at equilibrium by analyzing that delta G value. All right, the next question I have for you guys, going back to this equilibrium concept, is if we're looking at this, we know that it's not much of an equilibrium. It's going to favor the product side. Does that mean this reaction is going to occur quickly?
Yes. Not necessarily, actually.
You remember my discussion yesterday about how I'm going to eventually turn into carbon dioxide and water, but I hope that's not quickly or randomly. I hope that that's a slow process of going from starting material to product. How do we impact going from starting material to product?
The rate
That's murder. That's super morbid. What do we call that? The hump we have to overcome? Activation energy. So that's the other half of this equation is we look at delta G a lot of times. That tells us a lot about the equilibrium and where the reaction's headed. But we also have to look at how we get from point A to point B. So let's go and talk about kinetics now. So a spontaneous reaction does not always occur quickly.
I thought it was going to be quick.
How quickly will Jeff die?
No. If you wanted the question, like, is this going to happen quickly? You're like, oh, it's
All right, so how many of you guys remember rate equations? A little bit, a little rusty. So rate equations, we have this little k, not a big K. What's that?
The K.
Rate constant. So rate constant's little k. Oftentimes people draw in a big K. Big K is not used for rate constants. And then we have in our brackets some sort of reactant. Right, so rate constant is an important part. What do the brackets mean again? Concentration. This tells you essentially how quickly a reaction will occur. Why does concentration matter so much?
Because if you have more stuff hitting each other more often, it's like it's going to be faster to go.
Yeah, exactly. So, for example, I was at the dog park the other day with my puppy, and there were no dogs there, just my puppy. The concentration of dogs was low. The probability of my dog running into another dog, virtually non-existent. However, as soon as you increase the concentration of puppies in a dog park, they're going to be bouncing off one another like pinballs. So the concentration really matters a lot because a reaction is essentially like this giant air popper full of things flying around, and it relies on molecules hitting one another in order for a reaction to occur. So concentration is directly proportional to the frequency of molecular collisions. So let's make a note. When you increase concentration, you increase the frequency of molecular collisions. This means that things happen at a faster rate. All right, so that's a really important thing to remember is concentration is hugely important. All right? Not all rate equations are the same though, right? We've got some rates that are considered first order. And then we have second order. We have third order. What about fourth order?
Not really.
Doesn't happen very often. I can't even think of an example where it occurs. So first order, you've got a rate. This is multiplied by a rate constant, and you've got concentration of one thing. Another way of viewing this is it doesn't really rely on a collision between two different reagents. It's more or less the concentration of one reagent that determines the rate of a reaction, right? Oftentimes this is viewed as a decomposition, right? So if you've got a molecule that slowly falls apart just by existing, that could be considered a first order reaction. Second order. This now relies on the collision of two different reagents. So you can have either a collision of two different reagents, A and B, or you can have a rate where it relies on two reagents that are the same colliding with one another. And to show this, we do a squared. So in this case, two molecules of A running into one another could be a second order. And for the last one, we've got rate equals little k times a squared times b. What's another option for third order?
A squared.
Yeah, we could have a cubed, or we could have b squared times a. Really, the rate order is just the summation of all of your exponents. Whether that exponent is an assumed 1 or if it's a 2. Does that make sense? Most of this review? All right. So let's take an example and we'll try to determine the reaction order. So let's say we've got this example. All right, and I'm even going to make a chemical example for you guys. So I've got this compound plus I've got some base in solution or a nucleophile, depending on how you want to look at it. And in this case, we know from looking at this reaction that our products look like this, and my iodine is now an anion. Okay, so let's say I double the concentration of my nucleophile, but the rate remains unchanged. Whoop. However, if I double the concentration of my other starting material, the rate doubles. Let's try to come up with some sort of rate equation to explain what's occurring here. You guys can draw in the bond line formulas. You don't need to actually write the name. Be first order. Okay. So if we think about rates always have this small k. I've got a bracket. What goes in the bracket now? Would it be the thing with iodine or the sulfur?
The iodine.
Yeah, the iodine. Do I need to put the SH minus in brackets? No, because it doesn't impact the rate at all. So if we look at this, we can make an assumption that this reaction must be first order. In fact, we're going to cover this reaction in chapter 7. This is a substitution reaction. So if you look at that iodine, it was substituted with that SH. And if we look at this, it's specifically called an SN1 reaction. So SN1. And what this 1 means is that it's a first order substitution. There are examples of SN2. What do you think an SN2 reaction is? Second order. So maybe the concentration of both of them matters in an SN2 reaction. And we're going to talk about that a lot more when we get to chapter 7. It's important to remember that, though. Okay, so we've already talked about concentration and how that affects K, but let's go back to our little k. So what about little k, our rate constant? What affects this little k value? Does anybody have one thing that they think might affect the rate? So we just said concentration. We're only looking at little k separate from concentration. So what could change that little k?
Speed of the reaction.
Oh yeah, there's a lot of good ones being thrown out. So I heard temperature, I heard orientation. Catalyst is actually something a little bit different. We'll talk about that next though. But let's write down the few that we have. So we've got temperature. The way I think about temperature is how much energy do we have to climb this activation energy? If temperature is high, you've got a lot of energy, and that can help you overcome that energetic barrier. Number 2 is sterics. What does sterics mean? Yeah, the size. Another way of thinking about it is, let's say you've got 2 molecules, but they have to attack and hit each other in a specific orientation, like Athea was saying. If that molecule has a bunch of stuff hanging off of it, it can make that approach really challenging, right? So you can think about 2 molecules running into one another, but they need to be oriented correctly, and they need to have an accessible approach. So sterics is how accessible is the approach for the reaction or the collision. So I'll just do for the how accessible is the approach. All right, so we've talked about climbing the hill, how much energy we have, how approachable our route is up that hill. What's something else that matters in a very, very direct way? Yeah, exactly. How big is the hill that you have to overcome? So the third thing we want to look at is activation energy. So how big is the hill? So these are the 3 main things that affect that rate constant K. You have to consider all of these when you're looking at them. What's a trick we have for lowering the activation energy? And I'll put lowering in quotes. Catalysts. I don't really like this as a term for lowering, but I'll put it in there. And you said a catalyst, so I'll put that down. The thing with the catalyst is it's not actually lowering the activation energy for the reaction you're looking at. It's basically saying, why go over the hill? Let's find a different route.
The ways to map.
So why go over the hill? If you can find an easier route. That's the way I like to think about it. A good example is if you were in a wagon train in the 1980s, or not 1980s, 1830s. Wow, that makes me feel old. All right, so if you were on a wagon train and you were looking at a pass, you could say, well, the activation energy of going over that mountain is really high. That could be the shortest point from A to B. But oftentimes that's not what you're looking at. You're trying to find the lowest hill you have to overcome. So you're looking for those passes. A catalyst allows you access to some of those passes that have a much lower activation energy.
I was just going to ask, catalysts have to do with the way that they provide a surface for the reaction, correct?
They basically completely change the mechanism of a reaction.
So would that mostly affect the sterics?
It changes a lot with reactions. So let's draw an example where we've got delta G and we've got our reaction. And let's say I've got my starting material here. I've got my product over here. And normally this has a huge activation energy. So I'll write this line is without catalyst. The catalyst facilitates the reaction, and it changes the mechanism. And when you do this, the reaction pathway can change a lot. And oftentimes it'll involve, well, that kind of looks funny. it can involve one or more different intermediates. So now this activation energy, the largest hill we have to climb, is much, much smaller than without a catalyst. If you think about biology, our body uses a ton of catalysts when we do transformations biochemically, right? What do we call the catalysts in our body most of the time? Enzymes, right? So an enzyme actually changes the mechanism for these reactions. It facilitates the process of making and breaking bonds. All right, before we leave today, I've got another brain teaser. Let's consider this example. This used to be an in-class activity, but I wanted to do it as a group. Let's say we're starting right here in this well. And I've got two different pathways. I've got reaction pathway 1 that goes to the left, and I've got reaction pathway 2 to the right. Question I have for you guys is, how might you be able to favor the formation of product 2 over product 1? And how might you be able to favor the formation of product 1 over product 2? These are two competing pathways. You could go over either hill. But our goal is to specifically get product 1 or product 2. How can we control this? So I'll give you guys a minute to discuss this. All right, I'll stop you guys really quick, too. No catalysts.
Does that include inhibitors?
No inhibitors, no catalysts. All you got is your hot plate and a stir rod inside.
No, I would say concentration.
Nanomachines.
Nanobots.
Yeah. Black matter.
Jesus.
Well, if you throw like an excess of, so if you throw enough heat that it gets over into, but not enough that it can go backwards, then you can start favoring, and then eventually it would be just about falling. Yes, but then it can also go backwards, right? But if we throw enough heat to get over the activation 2, but not enough to get back to the product, so enough to get it on one side, but not enough to get it on the other.
If you have enough
That energy.
I just need to get, honestly, it's not complete, but I just need to get the temperatures, because I won't be able to get my lab up.
It's not a big enough jump.
All right, does anybody have a solid hypothesis for how to exclusively get product 2? Let's see if, is there anybody else? Brian's done a lot of contributions. What do you think?
Just add copious amounts of product 1 to the point where it super saturates it.
So let's say we're not manipulating the concentration. How could we favor the formation of product 2 without changing anything going into the flask? So no catalysts, no inhibitors, no changing concentrations. What do you think? For product 1 or 2? So for product 2, is it more stable or less stable? It's more stable, right? See, product 2 is lower in energy. That means it's more stable. Look at it this way. If we want to get our more stable product, should we have more heat or less heat? What do you guys think? You guys want to see a video? All right. All right, so for the first one, we're going to look at forming product 1. So this video is how can we exclusively isolate our less stable product? Oh, come on. Oh no, come on. Here, I'll open up my other notebook. Sorry, guys. All right, so for product 2, our less stable product, we'll take a look at this. And I'm going to do it in high speed because we don't got a lot of time.
Andiamo quindi a impostare una temperatura relativamente bassa. Vediamo la formazione prevalente dei prodotti del prodotto meno stabile dal fatto che sta aumentando la popolazione sul pianerottolo di sinistra. A questa temperatura il prodotto più stabile di destra si forma, ma non è attiva la reversibilità microscopica, cioè mentre le conversioni dai reagenti ai prodotti avvengono, anche se con scarsa frequenza, la conversione inversa dai prodotti ai reagenti non è cineticamente permessa.
What if we crank up the heat? Come on, internet.
Ok, partendo dalla stessa situazione iniziale, cioè tutti i reagenti del pianerottolo intermedio, ora ripeteremo la stessa trasformazione di due reazioni parallele, cioè la formazione di due.
Unusual happening. It does go over to the left-hand side.
Anche in questo caso abbiamo visto che solo inizialmente c'è stata una direzione privilegiata verso la formazione dei prodotti meno stabili. Il tasso di conversione ai prodotti più stabili è ancora più lento rispetto all'altro, significativamente più lento, perché la temperatura non è poi così elevata, quindi la barriera di sinistra viene superata ancora più frequentemente di quella di destra, a partire dai reagenti. La popolazione dei reagenti in questa fase è più o meno stabile, però anche se molto gradualmente si sta assistendo alla conversione dei prodotti meno stabili di sinistra verso i prodotti più stabili di destra.
We'll talk more about